Yeah, welcome. I'm Professor Webb, and this is my executive guide to artificial intelligence. So I might mention we're not going to get real detailed into a lot of the technology involved in artificial intelligence, but what we will do is dive down further enough so that an executive in a company can understand what the heck's going on inside the world of artificial intelligence and potentially how they can make it useful in their environment. So what is artificial intelligence? Well, it's the ability to acquire knowledge through learning and be able to take that knowledge and solve problems with it. So you use a program in this case, an algorithm typically developed in artificial intelligence to perform a task that usually requires humans, the intelligence of humans, wide ranging from a branch of computer science concerned with building smart machines and usually we're performing tasks that are typically require human intelligence, but we're trying to mimic that intelligence as best we can in the world of artificial intelligence. It's clearly an interdisciplinary science because we have uh, inputs from big data, we have inputs from algorithmic developments, and we have inputs from the world of like microprocessing. So all this is kind of coming together to be able to do things like machine learning and deep learning. Kind of a quick history of artificial intelligence. You can see here on this particular chart that the history goes all the way back to 1642. If we count the mechanical calculating machine that was built by Blaise Pascal in France, jumped to 1837, first designed for a programmable machine by Babbage and Lovelace. 19 jumped to 1943. Now we're starting to talk about neural networks, and we're going to dive into neural networks a little bit further into the presentation. But these become very, very important as we move forward in the world of artificial intelligence. But this is starting to parallel between the brain, how the brain operates, and how computing machines actually operate. By 1950, Alan Turing introduces what he calls the Turing test, and this is how you can test a machine's intelligence. 1955, artificial intelligence is actually called artificial intelligence for the first time in 1955. 1965, Eliza is it's a chatbot and it talks to you. It handles dialogue kind of on a very rudimentary level, but it's kind of similar to today's chatbots in that they can have a conversation. Jumping to the 1980s now, we have expert systems and we're starting to emulate decisions of human experts. 1997, Deep Blue computer developed by IBM beats world chess champion Gary Kasparov in a highly anticipated match. 2002, iRobot launches Roomba, and this is many of you may have one. Roomba is a vacuum cleaner that runs around the house and avoids obstacles and remembers where it has been and where it's going and vacuums your house while you sit around and do other things. 2009, Google builds the first self-driving car. Still working on that, but they had a prototype as early as 2009. 2011, IBM's Watson defeats a bunch of Jeopardy champions on the TV game show Jeopardy. 2011, 2014, personal assistants like Siri, Google, and other things start to be able to communicate with you a lot more effectively. 2014, we start to talk about the generative adversarial networks. 2016, AlphaGo beats a professional Go player. 2018, most universities have courses in artificial intelligence. And this is Alan Turing. We talked about him just a second ago. He's actually the guy who actually led the effort to break the Nazi encryption machine Enigma that helped the Allied forces win World War II. He's a mathematician, and he came up with a Turing test that just asked, "Can machines actually think?" And you can see there, Benedict Cumberbatch actually made a pretty decent movie about his life called The Imitation Game. Major advances, 1950s, the Turing test. 1955, we started to call it artificial intelligence. 1961, Unimate, the first industrial robot, goes to work at General Motors, replacing inmates, humans on the assembly line. And there you can see a Unimate there on the factory floor that was at General Motors. So here's some more major advances. Here's what ELIZA looked like, that in the lower left-hand corner. That was the chat box. It was pretty simple. It's not as complex as the ones that you see today. But you could ask it a question. It'd have a general conversation back and forth. Pretty rudimentary, though. 1966, Shaky. Is that those two gentlemen in the white shirts and skinny black ties were watching? That's the first electronic person, general purpose mobile robot. 1997, Deep Blue. There's Gary Kasparov staring at his chess pieces, and there's Deep Blue, who's already several moves ahead of him. And of course, Kismet, MIT, emotionally intelligent robot, and it kind of detects and responds to people's feelings. And you can see the lady putting together the final pieces to that. And then, of course, 1999, Consumer Robot Pet Dog. And things are getting pretty popular, especially among older people who find themselves alone in certain parts of the world. 2002, Roomba, a 2011 series integrated in by Apple. So it's a kind of an intelligent virtual assistant. You can actually talk to your iPhone and ask it questions. 2011, there's the IBM Watson winning Jeopardy. 2014, that's the Eugene, which is a chat bot that passed the Turing test with a third of the judges believing that Eugene was actually human, a human behind the scenes and not actually a chat bot. 2014, Alexa, that's over to the far right. You probably all have seen one of those around. 2016, of course, Tay, that's Microsoft's chatbot, goes rogue on social media and starts making all kinds of inflammatory and offensive racist comments, which is one of the problems with the big data, is that where does what's out there on the internet? Well, there's a lot of inflammatory and offensive racist comments. And when artificial and big data goes out and scrapes that information, unfortunately, it gets into some of these algorithms and gets all the way into the artificial intelligence model. And then I put a picture there of AlphaGo so you can see the difference if you're not familiar with a chess board, which should be familiar to most people. But the game of Go is dramatically more complex than chess. And it took them a lot longer, but now they do have programs that, AlphaGo can actually beat the world's Go champions. So here's the progression, 50s through the 80s. We had kind of early artificial intelligence, people are getting excited. Mostly it could play checkers, stuff like that. 1980s, 2010, we started to get into something called machine learning. And then deep learning from 2010 on. This is really, we're starting to drive a lot of breakthroughs, and this is where AI really starts to flourish. So here's the different levels: artificial intelligence, that's the general overall goal of being able to emulate a human being's reasoning faculties. Machine learning is within the field of artificial intelligence, and it confers the machine the ability to learn. They do this by using algorithms, and these algorithms discover different patterns and generate insights from the data they're exposed to. It can also be predictive as well. So deep learning is a subset of machine learning. And this is the most advanced AI field thus far. And this is how we can get artificial intelligence to think a lot more like a human. So here's machine learning. So it's one approach to bringing artificial intelligence forward. Eliminates or reduces the need to hand code a lot of software through lots of different possibilities. So through 1949 to the 60s, Arthur Samuel worked hard to evolve artificial intelligence from just basically recognizing patterns to actually learning from the experience of these patterns. So, and he used it using a game of checkers, okay? Current applications, a lot more sophisticated. And now we're even getting to medical applications. So, example, you can use large genome sets to prevent diseases and diagnose depression based on speech patterns and all kinds of other things. Most recent advances in artificial intelligence have taken machine learning, taking large data sets. So you can take a large data set and push it through these different algorithms. And then algorithms these days written mostly in Python, although there's some application for C and other Java and other languages. But it can make on the left, you can see it says it can make discrete, you can tell you what happened. At some point, it can actually give you an idea of what's going to happen in the future, somewhat predictive. And then it can actually become prescriptive, say, well, if this happens, you should probably do this, right? So you can build and build and build. The more data you have, and the more runtime you have, and the more data analysis you have, the more you can get toward actually figuring out what to do when you see certain things. So there's supervised learning. This is where a human actually labels a lot of the input. So, if I'm predicting housing prices, I can put in the time of the year and the interest rates and give it a lot more information and that helps define the output variable, which is housing prices and trends and things like that. So the algorithm's trained on this data to start to find the connection between the input that I had and the output that I'm requiring. So, and then once this training is completed, and I've kind of trained the algorithm what to do, usually you can start to bring in new data, and it can give you a pretty decent output. Unsupervised, that where I just put in a bunch of data. So it's unlabeled, it doesn't know what it is, and the algorithm can infer some sort of a structure from the data. And so this helps identify groups of data that exhibit any kind of similar behavior. This can actually be useful when you're not sure what you're looking for and you're just trying to look for different things. And sometimes some hidden information can pop out. So unsupervised learning can actually be pretty useful in certain instances. Machine learning, reinforced learning. So here, the algorithm takes an action from the environment. Like say it makes a trade in a financial portfolio, and then we see what it does. It receives a reward if the action is a step closer to maximizing total rewards. So it actually did pick the right stock or pick the right bond or whatever, and it actually went up and made the portfolio more robust. And so the algorithm here optimizes the series by correcting itself over time so that it continually does a better job of giving the proper output. You see this a lot on Wall Street with program trading and stuff like that. Machine learning. So we just talked about these, supervised machine learning, apply what you've learned in the past to new data that's being fed in. In contrast, unsupervised machine learning algorithms, that's when the information is used to train neither classified nor labeled. It studies how systems can infer a function to describe. There may be some hidden structure in there in the unlabeled data that we'll be able to get some information out of. Semi-supervised, that's somewhere between supervised and unsupervised, where we put some labeled data in there, a lot of unlabeled data in there, and just see let the algorithm work. And then, of course, reinforced machine learning is that way it interacts with the environment and changes a lot through errors or rewards based upon the outputs. So that's kind of the different ones. The trick here, though, is processing large volumes of information. The more information that the machine learning algorithms can get, the more accurate they're probably going to be. So here's how you can confuse machine learning a lot. When it first starts out, it doesn't sometimes know anything. And so one of the biggest uses of artificial intelligence these days is facial recognition. People use it in airports. It first was really big in the Orlando airport. As people came in, they did it there. And so the problem that they had was there's obviously all these different kinds of faces with all these different kinds of features and the different nationalities with different facial features from different nationalities. And so it can be really interesting when you're trying to pull all these together. And so this is just a good indication here when you're starting to pull in a bunch of pixels from a camera and putting that into your big data. What exactly is it do you have? And sometimes you have to tell it. Do you have a puppy dog? Or do you have a blueberry muffin? They look kind of the same at first glance, and the computer's not going to understand the differences. This is where humans are going to have to go in and label the data. This is a puppy. This is a blueberry muffin. Okay. And this is where you have to pull that together sometimes. There's all the different kinds of faces that are out there. And each different kind of face from different parts of the world. They all have, different features that a computer is going to have to learn how to read. And this is where facial recognition can get a little tricky sometimes. But this is where it needs to read a lot of faces to be able to be accurate. Okay, deep learning. So this is a type of machine learning, but now we can process a wider range of data resources. You need less data prepositioning by humans, and it probably is going to produce more accurate results than like the traditional data of machine learning that we just talked about. So, and in this case, we're going to be talking about software-based calculators known as neurons, and they form something called neural networks. So here's kind of a convoluted neural network, if you will. So we're going to try and find the letter A. So the camera goes out there and it takes a bunch of pictures and it kind of pulls together this pixelation, and you get this image and it starts to look like an A, and the hidden layer comes up and it says, okay, yeah, this is an A. So now from now on, the convolutional neural network can actually, say this is the letter A based upon. And so this is how the post office reads zip codes, and this is how handwriting recognition, you could take handwriting and put it into letterface and things like that. And so, now predictive recurrent neural networks, this happens on your phone a lot when you start to type in something, and the input is free, and it'll say, depending upon who you're talking to, your phone will automatically come up with something that says, are you free? Or it may assign, are you free tomorrow, which is the highest probability because you've asked somebody that a lot. So these recurring neural networks can sometimes just give the start of the sentence, are you? And it'll come up with free and then tomorrow on its own because, it's a recurring request that you've had. So, and then a lot of times, if you put out a survey, the survey in this case, you have to be very precise in how you put a survey together. And this is a mistake a lot of people make when they're putting together surveys, as they try and ask too many things in the same sentence, or it gives the customer ability to answer too many things in the same sentence. You have to be as specific as possible a lot of times. But if a restaurant just wants to ask, do you like the food? Does the customer like the food? So you ask. And then, but the customer wants to say, yeah, the food's great, but the service is terrible. And now you've got these extra words in there that you're going to have to filter through because you've got the word terrible in there. So food was great. So you can see there's, something that calculates the probability that the answer to this question is yes. In this case, 90% probability, yes. No, 5% probability, no. And then another 5% probability, I don't know. But the highest probability in this case is yes, just the way that the words were arranged. So, and there's your generative adversarial networks. The generator receives a penalty because it is able to fool the discriminator. So the discriminator receives a word because it recognized that the data was fake. So you've got real data, you're feeding it through, and you're able to tag fake data and be able to program your generative adversarial network that way. That's a deep learning technique. So as we dive into higher and more sophisticated levels, we have a lot more complex architecture that mimics a human brain. And this, in order to sense patterns, and even with noise and missing details and sources of confusion, you have to be able to do this. And what it takes is a lot more intelligence built into the system. So the image that I have on the right is, okay, the camera's going to go out there and it's going to take a picture of that, which is a dog inside of a blue circle in that case. And then it's going to come in and it's going to say, it's got two legs and it's got some sort of body, and has something that looks like a head. And then it figures out the edges, and then it looks at the combinations of the edges, and then it identifies the features. And eventually it's going to say, okay, this is a dog because we've got enough data to say these kinds of ears, this kind of nose, this kind of face, this kind of body, this kind of tail, and all that. In the early days, the table on the left, which has four legs and has something sticking out, that could be construed as an extra appendage. It could confuse those two things in the early days of being able to pull together your algorithm. So these are the things that you just have to work your way through and tag your data. So here's a nice little explanation of neural networks.
If you want your computer to recognize very complex patterns, then trust me on this. You really need to start using neural networks. When the patterns get really complex, neural nets start to outperform all of their competition. Plus, GPUs can train them faster than ever before. Let's take a look. Neural nets truly have the potential to revolutionize the field of artificial intelligence. We all know that computers are very good with repetitive calculations and detailed instructions, but they've historically been bad at recognizing patterns. Thanks to deep learning, this is all about to change. If you only need to analyze simple patterns, a basic classification tool like an SVM or logistic regression is typically good enough. But when your data has tens of different inputs or more, neural nets start to win out over the other methods. Still, as the patterns get even more complex, neural networks with a small number of layers can become unusable. The reason is that the number of nodes required in each layer grows exponentially with the number of possible patterns in the data. Eventually, training becomes way too expensive and the accuracy starts to suffer. So for an intricate pattern, like an image of a human face, for example, basic classification engines and shallow neural nets simply aren't good enough. The only practical choice is a deep net. Have you ever run into a wall when trying to work with highly complex data? Please comment and let me know your thoughts. But what enables a deep net to recognize these complex patterns? The key is that deep nets are able to break the complex patterns down into a series of simpler patterns. For example, let's say that a net had to decide whether or not an image contained a human face. A deep net would first use edges to detect different parts of the face, the lips, nose, eyes, ears, and so on, and would then combine the results together to form the whole face. This important feature, using simpler patterns as building blocks to detect complex patterns, is what gives deep nets their strength. The accuracy of these nets has become very impressive. In fact, a deep net from Google recently beat a human at a pattern recognition challenge. It's not surprising that deep nets were inspired by the structure of our own human brains. Even in the early days of neural networks, researchers wanted to link a large number of perceptrons together in a layered web, an idea which helped improve their accuracy. It is believed that our brains have a very deep architecture and that we decipher patterns just like a deep net. We detect complex patterns by first detecting and combining the simple ones. There is one downside to all this. Deep nets take much longer to train. The good news is that recent advances in computing have really reduced the amount of time it takes to properly train a net. High-performance GPUs can finish training a complex net in under a week, and fast CPUs may have taken weeks or even months. Before we talk more about the various deep learning models, we're going to briefly discuss which types of deep nets are suitable for different machine learning tasks. That's coming up in the next video.
Okay, so that was a little more in-depth and a look at neural nets and how they can enhance your artificial intelligence methodologies. So now we're going to get into artificial intelligence and combining all these things together. So we've got two kinds here. You've got narrow artificial intelligence. People call this weak AI. It's operates with a limited context and it's kind of a simulation of human intelligence, focused on like a single task. But then you've got AGI, artificial general intelligence. This is the kind of stuff you see on TV, Westworld, Data from Star Trek, Next Generation. So some examples that are really starting to come out of this are Google search, image recognition software, Siri, Alexa, self-driving cars, IBM's Watson. This is the stuff that really provokes the human imagination. So we're looking to look at three major areas of rapid advancement that have really kind of put AI on the map these days. One is algorithms. The second is this explosion of data. And then the third is the increases in computing power and storage. So here's algorithms. Okay, back in 1805, you know, okay, we have the groundwork for machine learning. Uh, wasn't until 1958 that we actually developed the first self-learning algorithm. 1965, deep learning. 1986, backpropagation. Uh, 1989, we talked about CNNs earlier for image recognition. 1992, we started to upgrade support vector machines. 1997, recurrent neural networks where we got a memory. We've gone over those things. 1998, if you don't know those two names, you probably should. Those are the guys who founded Google. What they did was they were both working at Stanford on their doctorates, and they found out that it was much easier to do what they call a page rank algorithm. What is that? So before they used to have this computer program to do search called Alta Vista was probably, there's a bunch of them, but Alta Vista was the most popular. But it would just give you a whole bunch of data, and you had to sort through pages and pages and pages of output to be able to find what you really needed, because there were no particular order. Just went and scraped the internet. What Brennan Page did was, they said, when you work on your doctorate, you have to be able to cite the people who are really the leading thinkers in your field. And you have to show that you know who all those people are, you know what they think, because you're trying to be one of them. You're trying to be a doctor yourself, right? And so what they did was they were able to go in and do a page ranking. So the number of in the academic world, and when you're doing your dissertation, it's who's been cited the most, you know, and in terms of what articles they've written, what speeches they've given, and if somebody's been cited 100,000 times, you definitely want to put them in your dissertation and refer to it. But in Alta Vista, you had to go through slowly each page and try and find these people. Well, they wrote an algorithm where they could page rank, where they could automatically go, these are the uh, websites that are most heavily linked and most heavily looked at by other people, so that they knew what the most popular uh, websites were. And so they wrote that algorithm and do it on Google, and then they put it on the Stanford computer system. Unfortunately, it got really, really popular among students, especially those writing papers and dissertations. So the university came to them and said, "Hey, you're eating up all our computer power. You need to take this off our systems." So they talked around, and eventually they, with the help of some venture capital, they were able to go out and form Google, and the rest is kind of history. So that's Brendan Page. So in 2006, of course, that's the deep learning models. We talked about the explosion of data. Previous to 1991, we used to have something called DARPANET, and I was on that when I was doing work for the Defense Department. And it was, you could go to different chat rooms and you could look at different things, and they had a browser. Eventually, at one point, the browser, Mosaic browser, was taken. Andreessen took it and popularized it on something called Netscape. And then CERN comes out with the World Wide Web, and now everybody can get onto the internet, what is now the internet. Before, the only people who used it were universities and different defense contractors and the government. But now it's exploded. So by the early 2000s, broadband comes along. 2004, Web 2.0. Now 2004, Facebook. 2005, YouTube. 2005, number of internet users passes 1 billion. 2007, iPhones. And then 2009, UC Berkeley introduces Spark to start handling big data. So there's all kinds of data out there, and all kinds of data that you can access, and everybody calls this big data, because the more data that you can get and use and analyze using your algorithms, the more accurate your findings are going to be once you run it all through, if you scrape the best data. Because as I mentioned before, the internet has got a bunch of stuff on there that you don't necessarily need in your analysis. So exponential increases in computing power. So this is the chips, right? Microprocessors. So 1965, Moore recognizes the exponential growth in chip power. He actually came up with something that we refer to in the semiconductor world as Moore's Law, which is the power of a microprocessor will double about once every 18 months. This is why you have to get a new computer about every 3 years, because the microprocessors, are doubling in power, and the people who write the software want the coolest software out there. And so they write to the cadence of these microprocessors. And because the microprocessors can, churn a lot more software data. And as a result, the software that's really utilizing the power of the microprocessor is going to be a lot more powerful and useful to a user than other software, right? So 1997, IBM's Deep Blue victory over Garry Kasparov. 1999, computing power for AI algorithms arise. No one knows that, but it's there. 2002, Amazon cloud storage. Now we can, it's easier to gather data, right? It's all in the cloud. 2004, MapReduce to cope with the data explosion that we've got. 2005, 1 gigabit of disk storage is now like 79 cents, which is 10 years before that, it was $277 for 1 gig. 2006, there's a store to process massive amounts of data. In 2007, NVIDIA introduces the Computer Unified Device Architecture for graphical processors. This was NVIDIA. If you haven't been following NVIDIA lately, it's exploded in people's uses of their chips, especially for artificial intelligence. So artificial intelligence, combining these three things together, 2009, graphical processors start to train deep learning modules. 2010, Microsoft and Google now have cloud computing. 2010, IP's Internet Protocol traffic exceeds 20 billion gigs. 2010, smartphones sold nears 300 million. So now smartphones produce what? More data. 2011, IBM, Watson beats Jeopardy. 2012, deep learning systems start to win image classification contests for the first time over humans. 2012, Google demonstrates deep learning for image recognition. 2012, also, Facebook hits 1 billion. 2013, faster training of word embeddings. 2013, DeepMind teaches an algorithm to play Atari. 2014, generative adversarial networks. In 2014, number of mobile devices exceeds the number of actual humans, because everybody has more than one device, right? 2017, electronic device users generate 2.5 quintillion bytes of data per day. This is the explosion of what they call big data. 2017, AlphaZero beats AlphaZero Go, learning to play 3 different games in less than 24 hours. This is the game of Go that I showed earlier. 2017, Google introduces upgraded TPUs that speeds the machine learning process. 2017, transformers that we showed the models earlier that improves language processing. 2018, Facebook opens PyTorch, and that speeds the develop of deep learning applications. 2018, now the European Union is starting to protect data because there's so much data out there, and people are starting to get upset that their data is out there. And so different governments are saying, hey, no, you can't just go take everybody's data. You have to tone it down a little bit. 2018, deep fake videos. And this is it's been a real problem. You're going to see them probably in elections. I know people do this to be able to, humiliate teenagers and all kinds of different things. 2018, Google brings BERT, which that improves natural language processing. 2020, ChatGPT, which is something that's really starting to explode and bring artificial intelligence to the next level. So here's total private investment. You can see it just going up and up and up. Private investment, autonomous driving, a lot of money going into autonomous driving. Cancer development, facial recognition software is huge. You're seeing it in cities. that have um, TV around, closed circuit TV around, and and also in airports and places like that. So fraud prevention and finance, and then the AI papers are published and they're just exploding. Everybody wants to be able to be known as an artificial intelligence expert. Trouble is, these machine learning projects, they take time. You got to cleanse the data, make sure it only gets the right data, get some of the nasty stuff out of there. You got to label it, you got to augment it, run it through, train the model. And it takes time to do all this kind of stuff. So just understand that you just don't pop data in there and just have it learn right away. If you're starting from scratch and you haven't got any data analyzed before, you're going to have to go through and do all these steps to be able to get to where you're getting some useful outputs. And then, deep and steep computing power just continues to explode. And all these different, now we're in what the modern era, about 3 to 4 months, we're doubling in our computing power in using training artificial intelligence systems. Forbes came up with something called mind-blowing things that AI can do. Can read articles and then report back essential information in a bunch of articles. I worked with a company for a while, a small company, where they did this for attorneys. What happened was they would feed a bunch of previous cases in, and then when that way they could feed a whole bunch of information back to an attorney who's getting ready to go to court. He had all the essential information he needed for that particular court case. People are using Chat GPT a lot these days to be able to write articles. And the articles aren't bad. Now, sometimes they come out a little clunky, and sometimes there's out and out errors in them, but it's getting better. Machine vision, where you can actually see the world, analyze visual data. There are things that obviously hear and understand, but things like detecting gunshots in certain neighborhoods, analyze it, alert relevant agencies. You can talk to Alexa, Google Maps. There are now models where you can, smell a human's breath and detect some kind of an illness, not just whether or not somebody's over the limit in drinking. Of course, touch. Either robots can go out and they can pick up an egg now, or squeeze a raspberry and find out if it's ready for consumption. Of course, you can move if you go to a factory floor, all kinds of movement from autonomous vehicles running around factory floors these days, bringing parts to different places. And you have drones now delivering packages. You have robots. Understanding emotions. You can track a person's emotions as they watch videos or as they speak. Of course, you can play games, chess, Go, poker. You can debate humans and complex subjects. Artificial intelligence is getting better at creating processes. They can make art. They can write poetry. They can compose music. None of it really hits the same level as humans yet. And of course, in some cases, they can actually read your mind. There are different people who they can put different devices, around on your skull and read brain waves and things, and actually, allow you to like work on a computer and things like that. So it's a little unnerving when you consider the mind reading aspect of this, but it's very helpful to people who are impaired. So, of course, in artificial intelligence manufacturing, we've got robotics, got autonomous vehicles. You can use it for quality control. You can go back and look at, okay, where did things start to go wrong, and start to pull data very quickly so you can get to the issue and quality very quickly. It can also give you predictive maintenance. What is your potential mean time between failure? When do you need to change out filters? When do you need to change out, blades, things like that? You look at just pure automation and being able to time things as they go through a factory. And of course, being able to figure out your supply chain and rearrange your supply chain in the case of where you've got some disruptions. Artificial intelligence can do this a lot more quickly than we have been able to do in the past. So overall, this is the AI is defined as the machine's ability to perform cognitive functions that we associate with human minds. So perceiving, problem solving, reasoning, learning, all these kinds of things. And so hopefully in the future, we'll be able to get better and better and better at artificial intelligence to solve business problems. You know, bring forward robotics and autonomous vehicles, computer vision, languages, virtual agents, machine learning, all these things, and make it work for us. Why now? As we mentioned before, algorithms are getting better and better. Explosion of data and the availability of data, but you have to scrub the data, as I mentioned. That's the downside. But at the same time, it's out there and it's available. If you can get it and you can analyze it, and of course, computing power and cloud storage, uh, those just enable things to move much more quickly. So you can do all this. This enhances your decision making. You can leverage this data, identify patterns and trends that sometimes are invisible to humans. You just don't notice. And you can do it quickly. You can do it effectively. Here are some of the components that we've talked about. Some of your applications: image recognition, speech recognition, chatbots, natural language generation, sentiment analysis, types of models: deep learning, machine learning, neural networks, software training, graphical processing units, parallel processing tools like Spark, cloud data storage, compute platforms, and then, of course, the different languages that you use. Python being the most recognizable, TensorFlow, of course, Java and C have been around a while. That's all I have. Contact me if you have any questions.